So this is, you see that it's basically the same proof we did last time. But last time we were assuming that some ratio was or we were assuming that this here converts to something. But you don't need it to converge. You just need that the Lieb soup is less than 1. And so likewise, if you examine what this case here say, then just like last time, it's going to say that if this here is bigger than 1, then the ordinary element doesn't even go to 0. Okay, so it fails the most basic test for being convergent. Okay, so, and that was just like last time also. And again, the advantage is, I think you were the one that was asking yesterday, yeah, I mean, like last time this with the ratio test and the root test, and like in the ratio test, it's something about that the next element is is going down with some fraction, right? And here, and you very much see that like this here works for all series, right? And it's really just because you don't compare the element to the next, but you're comparing it to this fixed series, which is the geometric series. Okay. So that's like the real version, so to speak, of the root test. So now let's talk a little bit more about power series. So, and I want to talk about, so like there's one function that is particularly important. And I mean, like all of these sort of basic functions are of course important, but they are somewhat similar. And the one I want to talk about is the exponential function. And there's various ways that you could define. So what is the exponential function? There's various ways that you could define the exponential function. You can define it, like 2 that comes to mind, but there's others too. One is that you could define it to be a function that's satisfying a certain differential equation. And that would be a good way of defining it. Another way of defining it, which is more relevant to what we're doing here, is defining it as a power series. So I'm looking at e to the x, and I'm looking at e to the x. So I define capital E of x as this power series that we looked at before. Okay. Now I want to prove that this here is really what you should think of. This here is the exponential function. So I want to show, but what does it mean that it is exponential? I want to show that this is the exponential function. So what do I mean by, I mean, of course I could define any function to be the exponential function. But there are certain properties of the exponential function that you would want, right? And so, well, the first thing I observe is that E of 0 is equal to, if all of these, if x is 0, then all of these are 0 except when n is equal to 0, and then x to the 0, this here is by definition 1. Okay, and this here is 0 factorial is by definition 1. So this here is 1 by definition. And we know already, by the way, that this here, we have already seen that the radius of convergence for this power series of convergence is equal to infinity, right? We have already seen that, right? So it's a well-defined function for all x, okay? Now, I'm later going to prove, so next time, we will show that if you define it like that this function here, defined like that, has a property that x e to x plus y is equal to this product here. Okay. Now, using this, well, the first thing I can observe is, I haven't really gotten to the property yet, but at the moment I'm just examining that particular function, some properties that it has. And so the first thing I will observe is that if x here is positive or non-negative, right, then all of these numbers are non-negative. So you're summing non-negative numbers, so the sum is non-negative. So if x is bigger or equal to 0, then it implies that e of x is bigger, is actually strictly positive. Right? In fact, the smallest one is where x was equal to 0, but in that case you got 1. Right? Now, if x here is negative, then it's not super clear. But if x is negative, some of these numbers that you'll be summing are positive and some of them are negative. So it's not at all clear what happened to the sum. But if you grant me this for the moment, this relationship here, then we would have that e to the x minus e in x minus x, so that's the same as, let me just make a little more space here. So e of 0, which I already know is 1. This here can think about that as x minus x, or if you will, you can think about it as x plus minus x. And now if you grant me this thing here that we'll prove next time, then I can write this here as e of x times e of minus x, right? Yeah. Okay. And now if x here is negative, then of course minus x is positive. So this thing here, so now I know by this thing here that this here is positive. And so since the product of these two things is 1, this here must be strictly positive as well, right? So this implies that e to the x is also strictly positive. Okay. So this is just a couple of observations. Now, of course, I'm using that relationship that I haven't established yet, but I will establish that next time. The next thing is that I want to define the number e. And so I define this. So e, that is 2.7 whatever, I don't remember. But so e, we define, so little e, so I define it as this function here evaluated in 1, okay? Now I want to define, so I have my function capital E, but I want to define a second function that is E. So want to define a second function and that is e to the x, like this, right? And that should have the kind of properties that you think it should have. Okay, so but first, before I do that, let me just think, if you take e to the power m here, m is, let's say that m here, let's say that m is an integer. If this here should just be e times e m times, right? Note that this here I can of course write as E. This is what E is. So I can write it as this here. M times. But now I can use this here that I will prove next time again. So if I take E of 1 times E of 1, then that's E of 2. And if I take E 3 times, then it's E of 3, right? So this thing here is actually the same as capital E of M, right? So I have that. I also, by definition, so E to the 0, this here I'm setting equal to 1, but I already have that 1 was equal to this capital E in 0, right? Okay, now what about if M here is a negative integer? So suppose that M here is a negative integer. Suppose that M here is negative. So, sorry, what should E to the M here be? This here is just 1 over E to the minus M. Okay, minus M is a positive integer, right? So this makes sense. Now, if you're looking at E to the, again, using this relationship here, E, the one, and in fact the one we just did. So this is on integers. This here is now equal to E of 0, which is equal to 1. And so this implies, and this is by that relationship over there, it's E of M times E of minus M. And so you see that this implies that E of minus M is equal to 1 over E of M by just dividing this on both sides. So you have this and this thing here, but this thing here, sorry, this is not what I wanted. If I take M negative, I just use the other one, sorry. E of M is equal to 1 over E of minus M. Like that, right? M was supposed to be negative, so this means that minus M is a positive integer. And this one here is then, this one I know that this here already agree with this little function of E. So you see that this thing here agrees with E to the power M, right? Right? Because we define it like this, and now I'm just checking that also on the negative integer, this function here and this function here agree. Okay, so I now have these two different functions. Well, one I haven't really defined yet. I've only defined it now on all integers. But so far, these two functions agree. Now, what I also should have is that I should have, so suppose you're looking at a rational number. So suppose you take a rational number. Remember, we usually write a rational number. So suppose that Q here is a rational number. We usually write a rational number as an element in set, so it could be negative, it could be 0, and N here is a positive integer. So a fraction like this. Now, what should E of Q be? Right? Well, E of Q, this here should be, right, how you would think about it is that it really should be something. It should be something this here should be a number alpha, and this should have the property that is positive, and it should have the property, so let's just write it, so E of Q, this is M over N, it should have the property that if you raise it, alpha here, suppose you were raising it to the power n, then you should get this number that we have already defined, right? So it should be positive, and when you raise it like this, then it should give you that. Right? And just like with square root of 2, there's just one element with this property. Okay, so that's defined. What it's so this way, you see, this way we have now defined this function E on all rational numbers. But now we need to check, right? We need to check that this thing here need to check. So that E of Q is equal like that, right? So I need to check that, okay? So I want to say that E to the Q is that alpha, right? So this means that I want to show, so I need to show two things. E to Q is positive. Well, I've already checked that, right? Because you checked at E, capital E at anything is positive. So this is okay. The second thing I need to check is that it has the property that if you raise it to the n power, then you're getting E to the m. Right? Now E to the m, that's an integer. It could be negative, but E to any negative integer, whether it's positive or negative, we already checked that this is equal to capital E of m. Okay? So now I need to, so this here is, so now what is this? So what do I need to check? So I need to check that E to the m over n, this thing here raised to the power n, is equal to this. But what is this here? This here is just E to the m over n multiply itself n times. So this is now n times. But now I can use again this thing that I proved next time, that when I do it like here, I'm just doing it 2 times, and here I'm just doing it for different x and y. But if I do it n times with the same x, then I'm just adding that x together n times, right? And so this thing here is the same as E by that rule over there, n times m over n, but this is just E of m, as it should be, right? So you see that these two functions here, so the conclusion so far is, so the conclusion now is that this function here is equal to this function here for all Q, for all rational numbers, okay? Now, what other property should this exponential, so this here, so far this is kind of the property that you want of the exponential function, right? But what other property should the exponential function have? It should have one other property, and that's enough to determine it, and that is it should be continuous. So one more property is that this function E to the x, when x is defined like this function should be continuous. And we'll talk a little bit more about continuous function in just a second. Okay, now then I have a theorem that we'll prove next time. One of the next times. And that is that suppose you take two functions. So we then can appeal to the following theorem. If f and g are two continuous functions, on R that agree on all of Q. So if you have two continuous functions and if you restrict it to the rational number, then the two functions are the same. If they're both continuous, then the function has to be the same. So this implies that f is equal to g everywhere, not just on the rational function, rational numbers. Fine. Okay, so we'll prove that either next time or the following time. Let me just go back and remind you about what it means for a function to be continuous. So this is the following. So continuous. So suppose you take a function, and the function it doesn't even need to be defined on an interval. But you may as well assume that it's an interval, but it doesn't need to be defined on an interval. So a function here, f, is said to be continuous at x here in the domain where it's defined if for all epsilon greater than 0, there exists delta greater than 0, such that if x minus x0 is smaller than delta, then the images are epsilon close to each other. And so again, this delta typically depends not just on epsilon, but also on x0. Right? And so the function, so it's continuous at a point x0, if this here is the case, and the function f here is said to be continuous if it is continuous at all points. Okay. Now let's look at two simple examples, and then once we have those, then together with some algebraic rules that are similar to the algebraic rules that we had for sequences, then we get a huge number of examples of, we get a large collection of examples of continuous functions. So the first example is like the simplest of all examples, where f here is the constant function. So I'm thinking about f here is defined from R into R, and for each x in R, it's equal to the same constant. Okay, so that's f. I want to show that this f is, that a constant function is continuous. So proof of continuity so given epsilon greater than 0, at this point stage you can pick any delta you want. I'm just picking, so let delta be equal to 1, but you could pick anything you want. It has to be positive, but you can pick anything you want. Then you have that if x minus x0 is less than 1, well then of course f of x minus f of x0, both of these numbers is c. So the difference, so this is c minus c, so this is 0. So this is surely less than epsilon, right? So this shows that the function is continuous at all points. And you see that you could pick delta anything you want. And of course, in particular, it doesn't even depend on x0. It doesn't depend on epsilon, and it doesn't depend on x0. Okay, so the constant functions are fortunately continuous. What about the next simplest function would be the linear function, or just x, function x. So suppose you're looking at the function f on R to R, where f of x is equal to x. So this is also continuous. Also continuous. And the proof of that, given epsilon, set delta equal to epsilon, then you see that if x minus x0 is less than epsilon, then f of x minus f of x0, but f of x is equal to x, and f of x0 is equal to x0. So this thing here is, of course, less than epsilon also, right? So this is, so that's kind of trivial, okay? Now the next thing is that we have the algebraic property of continuous functions. So we have some algebraic property. Properties of continuous function. And I will prove a couple of these. But the proofs, you see in just a second, that the proof is like, I mean, the properties is and there's good reasons for that. They're very similar to the property we had for limits of sequences, and the proofs are very similar to those proofs. So the first one is that if f and g are continuous, then the sum of these two functions is also continuous. The next one is that if f is continuous, and c is a constant, then c times f is continuous. The third property is that, again, if f comma g are continuous, then the product f times g is continuous. The fourth property is that if f is continuous and f is never equal to 0, then 1 over f is continuous. And the fifth property, that's a little bit different, and we didn't have that for sequences. The fifth property is that if you take a map f, or take a function f, the thing about it as a function from R to R, and then you have another function g from R to R. And now you could look at where you take first, you could look at the composition. So you could look at the function h of x, which is where you first apply f of x, f to x, and then you apply g to it. Right? So if both f, so if this here and the function g are continuous, then the composition here is also continuous. When you have a composition of function, you always have to be careful that it makes sense. So to make sense means that the function g, the second function that you apply, is that the image of, when you use the first function, you have to make sure that what you get here is at some point where g is defined. Right? So just for simplicity, I just looked at maps into functions into R, where g also was defined on all of R. But of course, it doesn't have to be defined, but you just have to make sure that g is defined where f and x end up. Right? Okay, I'll talk a little bit about, these, how to prove these, but it's very similar to what we did for sequences. Let me just apply it. So let me look at an example where I apply it. So suppose you take x squared plus 1. Suppose you take this function here. I'll take a look at two examples. Suppose you take this function here. I claim that this here is continuous. I'm not going to go through the proof, because we already actually, so if this here, we prove at least some of these properties. But once you have that, then you see that, well, you have that g of x equal to x. This here is continuous. This is what we proved just a little while ago. And if you take the function that is constant, and in this case constant 1, we already proved that that's continuous. Right? Now, this means that if you take a continuous function by whatever rule 3 or something like that over there, and you take the function where it's like multiplied by itself, this function here, right? Because g is continuous, this function here is also continuous. And then once you have that, you can add another. So you can look at d squared plus h. This is, you now have established that this is continuous. This is a constant function, so we already proven that this is continuous. So the sum by rule 1 over there, this here is continuous. Okay. So this means that, so this shows that this function here, this quadratic function, is continuous. But in fact, of course, this argument gives you that any polynomial is continuous. right? So this here proves that any polynomial, right? So this, like the similar argument, right? So if you're using, 1, 2, and 3, then just starting at the constant function and the function x, you can get to any polynomial and using these operations. And so it means that any polynomial is continuous, right? So you have the following theorem. All polynomials are continuous. Okay. And in fact, so this is just using 1, 2, and 3 over here. If you now also bring in 4, then you have, so this here is proof. Right, so it follows, it uses the 2 examples that we gave, and then in addition to that, it follows from the algebraic rules. One through 3. If you bring in also 4, 5 is something slightly different, but if you bring in 4 here, then you get that what's called any rational function. All rational function are continuous. So what is a rational function? A rational function is just where you're taking a polynomial and then you're dividing by another polynomial. Right, so we know that any polynomial is continuous. If you take another polynomial, and let's look at that other polynomial away from the roots, away from where it is 0. Away from where it's 0, this is, it's of course even continuous where it's 0, but you can't divide by it, right? So away from it, this function here is not 0 and is continuous. This here is continuous. Rule 4, so this is proved. The theorem above plus rule 4. Right? Yeah.
Earlier when you were showing that the function x.
Yeah. Yeah.
You chose your delta as a function of epsilon.
Yeah. In that case, exactly. In that case, I chose delta to be simply epsilon. Yeah. Yeah.
And you can use that for.
That's not a problem, right? It's just like if you give me an epsilon, then I have to pick a delta. And typically the delta will depend on epsilon. Typically it also depends on x. Let me give you an example of the last. I don't think I might not get to proving this, but that's fine. The proof, I'm not even sure I would go through it, but the proof is, maybe if I have a minute, I will talk about one of them. So let me give you an example also where, so typically it's highly unusual in the first example with a constant function that it doesn't really matter. You could pick delta anything, okay? Now, suppose you're looking at the function f of x equal to 1 over x. This is a rational function because it's a polynomial. In that case, the polynomial in the numerator is the constant function 1, and in the denominator is x. If you're looking at this function, let's just look at this function where it's strictly positive, right? And then you see now the graph looks basically like this. So in particular, if you go close to 0, it's not defined as 0, but if you go close to 0, then the image varies a lot, right? So if you take some fixed thing here, suppose you take So you want to prove that it's continuous at some x0. So this means that you have to pick some delta. So given an epsilon, you have to pick a delta so that if you are in this little interval, then the image lies in that little interval. But you see that as x0 becomes very close to 0, then in any small interval, the function varies a lot. So this means that if you take some fixed epsilon, then you expect that if the x0 was close to 0, then the delta had to be really, really, really small, right, for this to work, right? So typically, delta depends not just on epsilon, which it's highly unusual, it doesn't. It also depends on x. And in fact, if it doesn't depend on x or x0, then it has a particular name. We'll get to that later. It's called uniform continuity. Uniform continuity have some nice extra properties. And you will see later on that there's a good reason why the domain here did not include 0. If somehow this would have been a continuous function defined on an interval that included the endpoint, then actually it would automatically be uniform continuous. So it was at the good reason. This example here, it didn't include the point 0. Okay. Now let me just, so I have like 3 minutes left. Let me just talk about one particular of these. Like the first one and the second one is super easy. And the third one is also easy, and it uses exactly the same trick that we looked at before. So let me just talk about that for a minute, just because it's a little bit more interesting than 1 and 2 is barely interesting. So suppose I'm looking at the product of these two functions. And so remember that you give me an epsilon, I had to find a delta. So I have to find a delta so that this difference here is smaller. I want to find a delta so that if x minus x0 is smaller, if it's smaller than delta, then this difference here is smaller than epsilon. Right? That's what I'm supposed to do, just knowing that f and g are continuous. Right? And so I do, so this, just like when we had this for sequences, the similar thing for sequences, it's too much. It's too complicated if you just look at it like this. So what you do is that you take f of x times g of x, you insert something, and so you insert, it doesn't really matter which way you do it, but this is like halfway between this and that, where you take one point to be x0, the other to x. Of course, you didn't have that, so you have to add it again. But now the thing is that what you have done here is you sort of have split the difference, if you will. And so now, when you want to estimate this, you estimate this thing here first. So this is g of x times f of x minus f of x0. And you take the absolute value of this plus, and then this here you can factor out f of x0. G of x minus g of x0. And now you see, now you can sort of do like we did before. This here is now fixed, so you can also take the absolute value sign like that. And now this here is like just x0 is fixed, so this is just some fixed number. So this means that this thing here has to be maybe even smaller depending on what this constant is. But that's easy to achieve with some delta, right? Here it's a little bit more complicated because this one here is not fixed, right? But you have to then say that once you are close to x0, then this here, there's a bound for this. You see, it's sort of like what we did before. Right? So we are out of time, so I'll just leave it there. So next time we'll talk more about this with the exponential function. Yeah.
So are rational functions then to be continuous, or do we not call them continuous?
No, a rational function, any rational function is continuous. It's defined at points where the polynomial in the denominator away from the roots of the polynomial in the denominator. Right? It's continuous. One.
Are they said to be not continuous at the roots of the polynomial then?
One. Yeah, I mean, any rational function is continuous. It's just not defined at the roots. Okay. Now, for some polynomial, some rational functions, if you were sort of silly and you wrote, if you wrote this thing here, right? This is a polynomial, that's a polynomial. This one have a root as 0. But really, this function here, you would probably think about as being the constant function 1. Right? So it's still right. But it's not a priori, it's continuous away from the root. It doesn't say whether it's continuous at the root. It's just not defined at the root of the denominator. Yep.
If there's like one point it's not defined at, you just say it's continuous anywhere else.
Yeah, that's right. That's right. So that's right. So if you have a polynomial in a denominator, right, there's like finitely many points where you have roots, and at those points it's a priori not defined. You might be able to extend it in a continuous way to those points, but typically it's not defined in those points.